Okay, we want to talk about the Hubble Law, one of the most amazing and powerful tools that astronomers have devised for studying the distant parts of our universe. And we want to start by taking a look at this amazing image. It shows 5 different galaxies. And we're going to assume that the galaxies are all about the same size. We're going to start with the closest one to us, a galaxy in Virgo, this one right over here, and compare that to this other galaxy in the Big Dipper in Ursa Majoris. A more distant galaxy, roughly the same size, but if it's further away, it's going to look both dimmer and smaller as we see it. Same thing as we move to a third galaxy, a yet more distant one in Corona, further away still, and it looks much smaller and much further away. You know, these are not identical galaxies, obviously, but they're close enough and reasonably close. The one in the Big Dipper, Ursa, is a magnitude of about 16. We'd have trouble seeing that with the telescope at the Three College Observatory. The galaxy in Virgo, which is a mere 60 million light years from us, is pretty close, and we'd see that with binoculars or even a pretty small telescope. Go on down to Bootis, this galaxy further away still. See that little bitty circle right there? So dim you'd almost not see it, and that's further still. If we look at the galaxy in Hydra, you really don't even see it on this photograph. It's just a dim little speck, very, very distant from us, very, very far away. What do we see if you took a spectrum of these 5 galaxies? We'll start off by looking at the spectrum of the galaxy in Virgo here. And this is a spectrum right here. We're looking at a galaxy that shows us with violet or blue over on this side of the spectrum, red over on the right-hand side of the spectrum, the way we've been talking about. And we're going to look at a pair of little absorption lines right there. Those two. They should just be normally a little bit to the left, right over where I'm showing. And what we're seeing is that they've been redshifted by a small amount, almost too small to even be seen here. But the extent of their redshift tells us the velocity of recession for this galaxy pair, for this galaxy. And we can see that it's been measured by astronomers to be about 1,200 kilometers per second. And that leads us to understand that it's 60 million light years away from us. What we'd like to do is work through how that's done, but do it for the galaxy here in Ursa Majoris. And we can see that it's got a redshift that takes it's where it should be. That pair of lines should be right there. And it shifts it clear over to this place where you can see the pair of lines is. And that greater redshift moved it from about 393 nanometers here, which is in the purple or in the violet, over to kind of a blue color over here, 413 nanometers right there. And that leads an astronomer to calculate that its speed of recession is 15,000 kilometers per second. And we want to use that speed to work out how far away the galaxy is. If we went to a galaxy yet more distant, the one in Corona, you can see that it's got a much greater redshift. The pair of lines is clear over here. And it's got a 22,000 kilometer per second speed of recession. Go down to the Buddha's galaxy, way, way greater redshift for that galaxy pair. Clear over to here, a speed of 39,000 kilometers per second. The Hydra galaxy that's so distant that you can barely even see the thing, at least in this photograph, 61,000 kilometers per second. About 20% of the speed of light, an enormous redshift that takes that pair of lines that would normally be violet or purple clear over to almost into the yellow part of the spectrum. So what we want to do is work with this one. We're going to start with this speed, 15,000 kilometers per second, and we want to use the Hubble law to understand what's going on. So let's take a look at that, and here's what we're going to use. We're going to use the Hubble law. V is equal to hd. And if you remember from our discussions about that, this is the recession velocity, 15,000 kilometers per second, we've just been talking about. And this is going to be the distance of the galaxy, which we're going to find out. So this is known. That's known. The Hubble constant is known. And this is what we want to find. We want to find this value of d. Okay, and that's pretty straightforward. It's easy to do. 8th grade algebra is going to tell you that d is going to be equal to v divided by h, and we're just going to use that that expression and work this out. Now, h is 22 kilometers per second per million light years. We'll use an approximation of that just to make our divisions a little bit easier. We'll use 20 instead of 22. But what that means is that for every million light years away from us, a galaxy is moving about 20 kilometers per second faster in recession. So let's see how we're going to do this. We're going to put in the velocity, 15,000 kilometers per second. It's important that we pay attention to the units so we don't make a mistake in this. We're going to assume that h is 20 kilometers per second per million light years. And that's pretty straightforward. We can look at that and we can see that in the numerator and the denominator, both of them have got a kilometer per second. That means we can cross them out. Okay? And that means that the answer is going to be in millions of light years. So what's 15,000 divided by 20? Well, that tells us that d is going to be equal to about 750 million light years. Now, if you convert that into parsecs, that turns out to be around 230 million parsecs, 230 megaparsecs. And if we wanted to write that number in exponential notation, the way you've been doing all semester, that would be 2.3 times a mega is 10 to the 6th, but I had to move the decimal point 2 places to get to that, so it'll be 2.6 times 10 to the 8th parsecs. Okay? And that's a useful thing to know. Happens that that galaxy, if we measure it, has got an apparent magnitude of about 16 magnitudes. As I said before, that means it's pretty dim if we look at it in a telescope. But we can use that to find out what the absolute magnitude of the galaxy is, something we'd really like to know. How much light does it actually produce? And of course, the formula we use is the old familiar one that we've talked about before. We used it for stars before, but you could just as well apply it to galaxies. Is going to be equal to m minus m is going to be 5 times the log of d minus 5, and what we want to find this. That's what our goal is, and this is something we know. We know d and we know m. So let's do a quick switch over. That'll tell us that little m minus 5 times log of d plus 5 is going to be equal to big M, what we want. That's what we want to find. So let's just put the values in this. This will be 16 here minus 5 times the log 2.3 times 10 to the 8th, and then we're going to add a 5 over here. And if you work this out, this will turn out to be 16 plus 5, that's 21. Can I do that? Minus 5, and if you look up the log of 2.3 times 10 to the 8th, it'll come out to be 8.36. That means this will be 21 minus, if you work this out, 5 times 8.36 is 41.8. So if you divide those two, or you subtract those two numbers, that tells you that the apparent magnitude is minus 20.8. Pretty close to the absolute I'm sorry, this is the absolute magnitude. Pretty close to the absolute magnitude of our own Milky Way galaxy. So it's a galaxy that in size has probably got 200 billion, 300 billion, 400 billion stars in it. And we've used the same expression that we used earlier in the semester for stars, really just the inverse square law, to connect its distance to its true brightness and to its apparent magnitude.